It's a thought so massive, it almost breaks your brain to try and hold it all at once. For a little while, a single object from another star, an interstellar visitor sliding silently through our cosmic backyard, was enough to spark a sense of profound wonder, maybe even a little bit of unease. It was a statistical miracle, a one-off event. But what happens when we stop seeing it as a freak accident and start seeing it for what it might actually be? The beginning of something much, much bigger. It all started in 2017 with the first interstellar visitor we ever managed to confirm. A bizarre, elongated, tumbling object that astronomers named Oumuamua. At the time, it felt like winning the cosmic lottery. Then, just 2 years later, in 2019, came Borisov. This one was different. It was clearly a comet, burning bright with the chemical fingerprints of another, distant star. 2 visitors. The odds felt a little stranger. And now, we have Atlas. It's faster, weirder, and seems to be older still, racing through the inner solar system with a chemical signature, a blast of carbon dioxide that nobody was expecting. 3 confirmed visitors in less than 10 years. 3 knocks on our door from the great interstellar dark. This forces us to ask a question that we can no longer comfortably ignore. What if this isn't just a trickle? What if it's the start of a flood? What if Atlas, this strange new wanderer, is only the first of many, many more to come? Now, the calm, certain voice of science tells us not to worry. It points to celestial mechanics, to orbital solutions calculated down to the decimal point, to chemical spectra that break down the light from these objects into their constituent parts. The data, science says, is clear. These are natural objects. They're the leftovers from planet formation around faraway suns, kicked out by the gravitational chaos of their home systems, and left to wander the galaxy for billions of years. They pose no physical danger to Earth. Their flyby distances are measured not in thousands of miles, but in hundreds of millions. Safe, distant, unremarkable in the grand scheme of things. And yet, that scientific reassurance collides head-on with another, more primal instinct. A gut feeling that just refuses to quiet down. If we keep seeing them, if our ever more powerful telescopes keep snagging these cosmic vagabonds that were completely invisible to us just a decade ago, how long can we keep telling ourselves it's just a coincidence? How long before the comfort of statistics starts to feel less like a shield and more like a blindfold? It's right here, in the tense space between calm certainty and a creeping, gnawing paranoia, that our story truly begins. Astronomy tells us that, statistically, we should expect to see these things. Our models of how the galaxy works predict that there are literally trillions of these objects drifting between the stars. The vast majority are too small, too dark, and too far away for our current telescopes to ever see. But as our surveys get more sensitive, as our digital eyes get sharper, more and more of them are going to pop into view against the backdrop of our night sky. And while the cold, hard math frames them as nothing more than background noise, the inevitable cosmic debris of a messy galaxy, the human imagination can't help but fill that silence with a sense of unease. What if these arrivals aren't as random as we want to believe? What if their chemistry, which is already showing strange variations, or their trajectories, or even the timing of their appearances, hides a pattern we've been too afraid, or perhaps too arrogant, to even consider? For all of human history, the night sky has been a mirror, reflecting our own psychology. When something new and unexpected crosses that darkness, the temptation to read intention into the unknown is almost impossible to resist. For thousands of years, comets were seen as omens. They were messengers of disaster, heralds of war, famine, or the death of kings. Science, over centuries, methodically stripped them of that supernatural power, reducing them to what they are: magnificent but mindless balls of frozen rock, ice, and dust, orbiting our Sunday. But now, with these interstellar wanderers, it feels like we're right back at the beginning of that cycle. Our incredible scientific tools tell us these things are natural, but our ancient, pattern-seeking imaginations whisper that seeing one after another could mean something else entirely. The worst-case scenario is no longer just a random impact or a gravitational disruption. It shifts to something more subtle, more disquieting. What if each new arrival isn't just a visitor, but a signal? This is where the speculation really takes hold. Just consider the sequence of events. First, Oumuamua slides past, quiet, dark, and moving so fast that no spacecraft we could build had a prayer of catching it. Then Borisov follows, brighter, more obviously a comet, a little more normal, but still arriving and leaving before we can do much more than just watch it go. And now there's Atlas, with a chemical makeup so extreme it defies easy explanation, forcing astronomers to cook up theories that stretch the very edges of what we consider plausible. The line connecting these 3 points is short, but it is incredibly sharp. If 3 can show up in such a tiny sliver of time, how many more are sailing past us completely unobserved? And how many more are going to appear once the next generation of survey telescopes, like the incredible Vera Rubin Observatory, begin their work? The predictions are staggering. Once that observatory is fully operational, scientists suggest we might detect several interstellar visitors every single year. Let that sink in. We would go from the occasional, shocking interstellar event to a constant stream, a rolling, unending presence of alien material sweeping through our celestial neighborhood. The shift is profound. We'd move from isolated anomalies to a background hum of arrivals. And with that shift, the speculation will multiply exponentially. If these objects are truly random, they can tell us incredible things about how planets form around other stars, about chemistry written in distant stellar nurseries billions of years before the Earth even existed. But if they're not random, if the frequency itself becomes the signal, then the implications stretch far beyond the realm of astronomy. They start to raise questions about intention, about surveillance, maybe even about contact. Suddenly, the chilling possibility emerges that the galaxy isn't silent at all. Maybe it's communicating, but it's doing so through objects so ancient and so perfectly disguised as cosmic junk that we've been mistaking them for simple chance and debris all along. This line of thinking isn't born from wild conspiracy or baseless panic. It comes from the exact same place of curiosity that drives every single scientific discovery. The only difference is that it allows for the possibility that the unknown might be more than just a statistical surprise. For every carefully crafted explanation grounded in chemistry and orbital mechanics, there's a shadow version of the story where each arrival hints at something much, much larger. The natural models say these visitors are the scattered leftovers of planet formation. The speculative mirror suggests they could be probes, a quiet census of developing civilizations, or even seeds of something we can't yet begin to define. The tension between these two ways of seeing is not easy to resolve, and maybe, just maybe, it never will be. When astronomers first pointed their instruments at that faint, blurry streak of light they named Atlas, they weren't just seeing an object from deep space. They were seeing the absolute limits of their own tools reflected right back at them. Every single telescope, no matter how powerful or advanced, is fundamentally a filter. It gathers up the faint light from the cosmos, passes it through lenses and mirrors, stretches it out into a rainbow of chemical spectra, and translates the raw, chaotic hum of the universe into patterns that our human minds can actually work with. But filters don't just reveal things, they also obscure them. And somewhere in that vast, dark abyss between the photons that manage to reach our detectors and the conclusions we draw from them, that's where the shadows live. 3 interstellar visitors in less than 10 years? Statistically speaking, this shouldn't have been a surprise to anyone in the field. For decades, our models of how planets form have suggested that the galaxy ought to be absolutely teeming with this kind of debris. The process of building a planetary system is incredibly violent and chaotic. It's a cosmic game of billiards, where countless chunks of ice and rock get flung out into the interstellar void. It's a messy birth, and that mess gets scattered across the galaxy. And yet, when Oumuamua showed up in 2017, it sent a shockwave through the entire world, precisely because nothing like it had ever been seen before. The surprise wasn't that these things were rare, but that our instruments had been completely blind to them until the very second one strayed close enough for us to finally notice. And that blindness wasn't just a technical limitation. It was a conceptual one. For centuries, astronomy treated the vast spaces between the stars as fundamentally empty, clean, and silent. Now, we're being forced to accept that the silence was just an illusion created by our own deafness. But even with this new knowledge, the question of what we're still missing remains sharper and more unsettling than ever. Every single detection we make carries with it a margin of error, a kind of fuzziness around the absolute truth. And Atlas is no exception. We know its orbit is hyperbolic, meaning it's not bound to our Sunday. We know its chemistry is unusual. We know its speed is extreme. All of those things are measurable, but they're measured through layers and layers of inference and interpretation. A faint glow on a digital detector becomes a single data point. A cluster of those points becomes a curve on a graph. That curve is then fitted to complex equations describing celestial motion. A spectrum is painstakingly drawn from its light, and that spectrum is then bent through complex models of how molecules absorb light. Each step in this process adds confidence, but it also adds risk. And the shadows in the data? They live in those in-between spaces, where interpretation can bend in more than one direction. When scientists say that Atlas is a natural object, they're speaking with the full weight of the available evidence. The cloud of gas, or coma, that it's shedding is consistent with ices turning directly into gas under the sun's heat. The patterns of light emission align with molecules we know and understand. Its trajectory fits cleanly within our expectations of how gravity works. And yet, when you look really closely, the numbers don't fit perfectly. The concentration of carbon dioxide is extreme, well beyond the typical range we see in comets from our own solar system. The almost complete absence of a strong water signature at large distances from the sun is deeply puzzling. These are anomalies, and anomalies are the breeding grounds for speculation. They're also, historically, where the most important scientific discoveries have often been hiding. Pulsars started out as inexplicable, perfectly regular radio pulses. Quasars just looked like weird stars until their massive redshifts proved they were something else entirely. The cosmic microwave background radiation, the echo of the Big Bang itself, was initially dismissed as interference from pigeon droppings in a radio antenna. Shadows in the data can be brushed aside or they can be embraced, but they very rarely just vanish on their own. For every astronomer calmly noting that this unusual chemistry can probably be explained by some natural process we don't fully understand yet, there's another, quieter voice wondering if these anomalies aren't signs of randomness at all, but signs of design. The human brain, which evolved to detect patterns in the rustling grass of the savannah just as much as in the starry skies, really struggles with the idea of pure, unadulterated coincidence. If Atlas is just one single data point, then maybe an anomaly is to be expected. But if Atlas is part of a growing trend of strange visitors, then anomaly starts to look a lot more like signal. The shadows aren't just in the light curves and the spectra, they're in our own interpretation of what we decide counts as meaningful. The very tools we use also shape the shadows we see. Ground-based observatories have to fight against the distortion of Earth's atmosphere, which turns a pinpoint of light into a smeared, blurry image. Space telescopes like Hubble and the James Webb avoid that problem, but they face their own limitations of time, field of view, and sensitivity. No single instrument can ever capture the whole truth. Hubble is a master of visible and ultraviolet light. The James Webb Space Telescope peers deep into the infrared. Radio telescopes scan the long, slow wavelengths. Each one produces a single piece of the puzzle, but no single piece can ever explain the whole thing. When Atlas was analyzed, data from the Webb telescope suggested a high dominance of carbon dioxide, while other instruments picked up signals that looked a little more conventional. The datasets only partially overlapped, leaving gaps where interpretation became a form of educated guesswork. And those gaps are exactly where speculation loves to creep in. In their public communications, scientists are incredibly careful. They emphasize certainty because certainty is reassuring to the public. NASA and the European Space Agency will repeat, like a mantra, that Atlas poses no danger, that its path is well understood, that its chemistry, while odd, is not impossible to explain naturally. But in the internal, private conversations of astronomy in the hallways of universities and during late-night conference sessions, the tone is different. The questions are sharper. Why this much carbon dioxide? Why this velocity? Why this frequency of detections when our older theories said we should see so few? Professional caution prevents these questions from ever making it into the headlines. But the questions remain. The shadows are just as much cultural as they are scientific, shaped by the institutional pressure to maintain authority and avoid feeding public panic. This gap between public certainty and professional curiosity is critical, because it's in that very space that paranoia finds room to grow. When the official statements all emphasize safety and natural explanations, some people will inevitably assume that the strange parts, the anomalies, are being deliberately hidden. Conspiracies thrive in the shadows, not because there's any evidence to support them, but because uncertainty is an open invitation for the imagination to run wild. Atlas is a perfect case study in how data that appear mundane and technical to experts can spiral into the most exotic speculation outside of professional circles. When the numbers don't fit perfectly, the stories multiply. Some will speak of alien probes disguised as comets. Others will whisper about surveillance disguised as random trajectories. Most of these ideas collapse under the slightest bit of scrutiny. But scrutiny itself rarely travels as far or as fast as speculation. The real challenge here isn't just proving what Atlas is, but trying to prove what it is not. The evidence for it being a natural object is abundant. It's everywhere. But a lack of artificial signals doesn't prove a lack of intent. Our radio telescopes have scoured it for any hint of a coherent transmission, but they've found nothing. But maybe, just maybe, no signals were ever sent. Our analysis of its trajectory shows no signs of controlled maneuvers, no little course corrections. But maybe none were needed. Its thermal profile, the way it heats up and cools down, aligns perfectly with what you'd expect from solar heating. But maybe any active systems are so well shielded that we'd never see the heat, and so, in this frustrating way, the shadows persist. No matter how thorough our analysis is, the possibility of what we cannot detect will always remain. That's the fundamental paradox of these interstellar visitors. We can only study them for a brief, fleeting moment, at immense distances, and then they just vanish back into the interstellar night forever. Each one becomes both a solved mystery and an eternal question mark. Looking back at Oumuamua, you can see the exact same dynamic at play. Its bizarre, elongated shape and that slight, non-gravitational acceleration were eventually explained by scientists as being consistent with natural outgassing from a tumbling, nitrogen ice body. But for some people, those explanations felt like a stretch. For others, they felt like satisfying closure. The shadows in that data remain, even as the object itself races away from us, never to be studied again. Borisov was more straightforward, a textbook comet. But Atlas is both comet-like and anomalous, a perfect mixture of certainty and mystery. The pattern here isn't one of clear, satisfying resolutions. It's a pattern of recurring, nagging questions. Each new visitor adds to the mountain of data, but it also deepens the sense that the shadows will never disappear entirely. This leads to a much larger, more profound concern. If Atlas is only the first of many, then the shadows in the data are only going to multiply. Every new detection will bring its own set of anomalies. Some will be chemical, others will be orbital, others will be purely observational quirks. Individually, each one might be explainable, but collectively, they might start to point towards something we don't yet have a name for. It's one thing to dismiss a single comet's weird chemistry as a fluke. It's another thing entirely to dismiss a dozen similar cases across a dozen different arrivals. Patterns only emerge through repetition, and repetition is exactly what the future is promising us. The next generation of sky surveys will deepen this process exponentially. The Vera Rubin Observatory, with its incredible ability to scan the entire southern sky every few nights, is going to flood the field of astronomy with new detections. The predictions suggest that several interstellar visitors per year will soon be added to the catalogue. Each one will be studied, each one will display its own unique quirks, and each one will cast its own shadows of uncertainty. The scientific value of this is immense. We'll be getting glimpses into planetary systems far beyond our own, seeing chemical diversity on a galactic scale, and studying histories older than our own solar system. But alongside that incredible value lies the inevitable. Speculation will grow in direct proportion to the number of anomalies we find. The more shadows we find, the more people are going to ask what they're hiding. This is the pivot point. This is where science and paranoia meet. Shadows in the data aren't flaws, they're opportunities. But they also invite interpretations that escape the tight leash of evidence. In that sense, the greatest challenge of all these future interstellar detections might not be a technical one, but a psychological one. How will we, as a species, handle the coming flood of uncertainty that arrives with each new object? Will we learn to accept these anomalies as just part of nature's incredible, beautiful diversity? Or will we start to see them as coded signals, as signs of surveillance, as harbingers of intentions that are not our own? Atlas is not just a comet, it's a rehearsal. The way we choose to interpret its shadows will fundamentally shape how we interpret the many that are destined to follow. Already, the debates are rippling through scientific conferences and research papers. Some are pushing for more aggressive searches for artificial signals, what we call SETI. Others are warning against fueling what they see as baseless speculation. Some argue that even considering the possibility of design undermines public trust in science. But others counter that avoiding such questions blinds us to possibilities we simply cannot afford to ignore. The shadows demand our attention, but the act of paying attention itself changes the story. The simple truth is that the shadows in the data will always be with us. No instrument is perfect. No measurement is completely free of error. No interpretation is immune to human bias. Atlas, just like its predecessors, embodies that truth. It is, at once, a clear-cut comet and a giant cosmic question mark. It's a visitor from the galactic dark that reveals just as much about our own limitations as it does about itself. And as we prepare ourselves for the many that will follow, we're being forced to confront not only the mysteries of the objects themselves, but the shadows in our own methods, in our own minds, and in our own deep-seated need to find meaning and patterns in the chaos, patterns that may, or may not, actually exist. The journey continues, not just with the next object that appears, but with the recognition that every single observation is also an invitation to confront our own uncertainty. Each detection is a humbling reminder that our instruments are powerful but imperfect, and that our interpretations are grounded but fragile. And in that fragile space, between the light we collect and the meaning we assign, the shadows will always be waiting. By the time astronomers officially confirmed Atlas as the third interstellar visitor, the entire frame of the conversation had already shifted. You could no longer point to a single, isolated discovery and just call it an anomaly. The profound silence of centuries had been broken, not once, but repeatedly, and in quick succession. First, Oumuamua in 2017, then Borisov in 2019, and now Atlas in 2025. Now, in strict, cold, statistical language, 3 data points might not be enough to constitute a definitive trend, but in the court of human perception, it's more than enough to completely redefine our expectations. Where once the very idea of an interstellar wanderer sailing into our solar system seemed like something out of science fiction, it now seems almost inevitable. The real question is no longer how extraordinary these 3 visitors were, but how many countless others passed by completely unnoticed before our instruments were finally capable of seeing them. It's worth remembering that Oumuamua was discovered almost entirely by accident. A routine sky survey, designed to spot near-Earth asteroids, just happened to catch a faint, moving point of light that didn't fit any of the expected orbital shapes. Borisov, which was brighter and more obviously comet-like, was first noticed by an amateur astronomer using a relatively modest telescope, highlighting the very real possibility that many of these visitors could have slipped right through the professional nets without anyone ever realizing. Atlas, for its part, was spotted by a dedicated survey program, the kind designed precisely to scan the sky, night after night, looking for new and unusual objects. The pattern is crystal clear. The only reason we now have a catalogue with 3 confirmed interstellar visitors is because our methods of watching the sky have dramatically improved. This raises an obvious and slightly unsettling conclusion. If our tools have only recently, in the last decade, reached the level of sensitivity required to detect such objects, then the 3 we've seen are not exceptional intruders. They are merely the first representatives of a vast population that has always been there. And that population must be absolutely immense. Our best models of how planets form predict that every single star system, during its chaotic and violent early evolution, expels a vast number of icy and rocky fragments. The gravitational billiards played by giant planets, the tug of companion stars, and the close passes of other stars all work together to throw debris outward, scattering it like seeds into interstellar space. Now, multiply that process by the hundreds of billions of stars across our galaxy, and the number of wandering objects becomes almost unimaginable. What we've managed to see so far is only the faintest, tiniest tip of a colossal iceberg that extends throughout the galactic dark. This realization completely changes the scale of the problem. If there are literally trillions of interstellar objects drifting between the stars, then it's not surprising that some of them wander into our neighborhood. In fact, it would be far more surprising if they didn't. What's truly unusual is not their existence, but the fact that we have been completely blind to them for so long. Until very recently, our telescopes simply lacked the raw power to detect these faint, fast-moving points of light against the glittering backdrop of the stars. It's only with the advent of wide-field, automated surveys, combined with advanced algorithms capable of flagging unusual trajectories, that the floodgates have finally begun to open. And if 3 have been found in less than a decade, then dozens, maybe even hundreds, should be well within our reach in the coming years. And yet, statistics alone are not enough to quiet that creeping sense of unease. For each new object that appears, the temptation arises to ask whether its arrival is truly, genuinely random. We tell ourselves that they are just scattered debris. But human perception is primed, it is hardwired, to interpret repetition as a pattern. 3 confirmed visitors in such a short span of time feels like something more than mere chance. Even if the mathematics of probability insists otherwise, that tension is only going to grow as the number of detections multiplies. When the 4th and the 5th and the 10th interstellar visitor are found, the story will no longer be about anomalies at all. It will be about the constant, unending presence of countless unseen wanderers, silently and perpetually sweeping through our solar system. Most will be too faint for us to ever notice, but they will all be there, passing through the skies above our heads. Astronomy thrives on sample size. With only one interstellar visitor, Oumuamua, every single anomaly was amplified. Its elongated shape and strange acceleration became global mysteries, debated endlessly by scientists and the public alike. With 2, Borisov's more conventional, comet-like nature suggested that there was a diversity among these wanderers. With 3, Atlas's unusual chemistry has sharpened the contrast even further. Once the number of detections grows larger, patterns may begin to emerge that finally resolve these questions, showing us the full range of what is normal for such objects. But until then, each new detection carries a disproportionate amount of weight. Each one is treated as both a messenger and a mystery, and in that dual role they embody something more than just science. They embody our deepest speculations about what lies beyond our cosmic shores. It's right here that the phrase "countless unseen" takes on a meaning that goes far beyond simple statistics. If the vast majority of interstellar wanderers remain invisible to us, then our picture of the galaxy is fundamentally incomplete. Every confirmed visitor is not just an isolated object. It is a stark reminder of the immense number that we miss. And this ignorance is not benign. Consider for a moment that some of these wanderers may be far larger than Atlas, with rocky or icy nuclei stretching for tens of kilometers across. Others may be moving at even greater speeds, leaving only the faintest and most fleeting of traces behind them. Some could be carrying exotic chemistries that completely defy our understanding of how planets are supposed to form. Others might come close enough to Earth to raise serious questions about impact risk, even if the overall probability remains low. By definition, we don't know what we're missing, and that ignorance is both profoundly humbling and deeply unsettling. The unseen also invites another, more speculative, kind of thinking. If these wanderers are truly countless, then it is statistically possible that a small fraction of them may not be natural at all. Even if 99.999% of them are just boring fragments of ice and rock, the remaining tiny fraction could represent something else entirely. A probe, perfectly disguised as debris. A device, engineered to survive across billions of years of interstellar travel. Or even just a silent drifting relic of some advanced civilization that has long since vanished. The odds of us ever encountering such an object are, of course, infinitesimally slim. But when the total population is measured in the trillions, even slim odds can translate into very real possibilities. Every single unseen wanderer carries with it not just scientific data, but the possibility, however faint, of something profoundly and fundamentally different. This is the very heart of the unease. We can model the populations, we can calculate the detection rates, and we can predict future discoveries with a high degree of confidence. But the possibility of encountering something that exists completely outside of our models will never, ever disappear. The unseen hides both the mundane and the extraordinary, and until each object is actually observed, we can never truly know which it will be. The shadows in the data, which were already troubling, grow 1,000 times deeper when you multiply them by these countless unseen companions. What makes this situation so unique is its absolute inevitability. Unlike other cosmic mysteries that require extraordinary conditions or incredibly rare celestial alignments, the arrival of interstellar objects is guaranteed. They are not rare, spectacular fireworks lighting up the sky once a century. They are the constant background noise of the galaxy. We're not waiting for some improbable event to occur. We are simply waiting for the continuation of a process that has been happening all along. The only thing that has changed is our awareness. And awareness changes everything. The idea of these countless unseen wanderers completely reframes our relationship with the galaxy. No longer can we think of our solar system as some isolated, self-contained system, drifting quietly and safely through the void. Instead, it becomes a part of a constant, flowing traffic pattern, a node along ancient routes traced by debris that is billions of years old. These visitors are not occasional intruders. They are constant, silent reminders that our cosmic neighborhood is porous, that material from distant, unknown stars passes through our home without invitation and, until recently, without notice. The interstellar medium, the space between the stars, is not empty. It is a vast, dark ocean of fragments, and we are only just beginning to glimpse the waves. In this ocean, the 3 confirmed visitors are like the first few ships sighted from a lonely shore. Each one is a hint of much larger, more complex traffic patterns that exist just beyond the horizon of our vision. We may never know how many passed unseen in the centuries before our telescopes were strong enough. We may never even know how many pass unseen right now. But what we do know is that as our instruments get sharper, the number of confirmed sightings will rise. And with each new arrival, the tension between statistical certainty and speculative unease will only get deeper. Because every new object confirms the sheer vastness of the unseen, and every single anomaly hints at meanings that lie beyond the natural. The challenge for astronomy is to somehow balance these two truths. On the one hand, the population of unseen wanderers is a scientific treasure trove. Each one offers a precious sample of alien geology, a tiny fragment of chemical history from a different star altogether. Together, they can help us map the incredible diversity of planet formation across the entire galaxy. But on the other hand, this same population is a fertile breeding ground for speculation, because every single detection comes to us filtered through incomplete data. Each object vanishes back into the dark before we can ever hope to study it fully, leaving a trail of unresolved questions and untested suspicions. The countless unseen may carry more answers than we can ever hope to extract. And it's in that gap, between what we know for sure and what we can imagine, that speculation will always thrive. What emerges from all of this is a picture that is both deeply reassuring and profoundly disquieting. It's reassuring because the coming flood of interstellar visitors proves that we are not truly isolated. Material from all across the galaxy flows through our system, carrying with it knowledge that we can actually study. But it's disquieting because each new detection is a stark reminder of the many more that we will never see, and of the incredible possibilities that may be hidden within them. The delicate balance between science and speculation, between certainty and paranoia, will only become sharper and more precarious as the numbers continue to rise. And rise they will. Because the 3 confirmed visitors are not the real story here. The real story is the countless unseen, waiting out there in the dark, moving silently across the galaxy, slipping past our instruments, until the very moment one of them appears in our field of view and forces us once again to ask what its presence truly means. When astronomers really start to confront the scale of these interstellar wanderers, the numbers quickly lose their ability to shock. It all begins with simple probability. A single planetary system like our own produces countless fragments of ice and rock during its chaotic formative years. Most of these fragments are consumed, crashing into planets, moons, or the star itself. But a small fraction are flung outward, accelerated by gravitational encounters until their orbits exceed their star's escape velocity. They drift away, carrying with them the chemical fingerprints of their origins, and once they're freed, they never return. Now, multiply that process by hundreds of billions of stars in the galaxy, and the result is just staggering. The galaxy shouldn't just contain interstellar wanderers. It should be absolutely overflowing with them. The discovery of 3 confirmed visitors so quickly after we started our systematic surveys aligns perfectly with this prediction. Far from being strange outliers, they are the early representatives of a population that must number in the trillions. Oumuamua, Borisov, and Atlas are not unique jewels that we stumbled upon by accident. They are the first few drops from a downpour that has been falling for billions upon billions of years. The statistics demand it. The probability of our solar system somehow avoiding these kinds of encounters for eons is vanishingly small. The only reason it seemed so quiet until now is because we were blind. Our instruments simply lacked the precision to see these faint lights racing across the sky. So, we assumed the sky was empty. Once you lay the mathematics bare, the illusion of rarity completely collapses. Researchers can model the expected density of interstellar objects by working backward from the detections we already have. If 3 have been spotted in less than a decade of serious surveying, the implied number of objects drifting through the galaxy at any given moment must be astronomical. For every single one large enough and close enough to be noticed, there may be millions, or even billions, more that are too faint to see. Some estimates suggest that at any given moment, tens of thousands of such wanderers are currently passing within the orbit of Neptune. Most of them are no larger than boulders, far too small for our current telescopes to ever pick up. But they are there, nonetheless. Silent and invisible. This statistical certainty completely reframes the story of Atlas. Its chemistry might be unusual, its velocity might be extreme, but what matters most is that its very detection confirms a much larger truth. Interstellar objects are not rare visitors. They are constant companions. The solar system is not an isolated bubble floating in some sterile void. It is a crossroads on galactic highways, trafficked by debris that is older than our own Sunday, and once that traffic is acknowledged, the next step is inevitable. We have to ask not only how many there are, but what kinds of stories they carry. Probability alone suggests that among trillions of wanderers, the diversity must be absolutely immense. Some will be icy comets, just like Borisov, their surfaces still rich with the volatile compounds from their birth. Others will be dry and rocky, more like Oumuamua, their ices having been burned away long ago by their home star or the ravages of time. Some will be enormous, dwarfing any comet we've ever catalogued in our own system, while others will be nothing more than dust-sized fragments, scattered invisibly through space. Their chemistry will vary depending on their stellar environment, reflecting the abundance of carbon, oxygen, nitrogen, and metals that were present when each system formed. Some will carry water, others exotic ices like methane or ammonia, and still others may contain complex compounds completely unknown to us here on Earth. With numbers this vast, the range of possibilities is limited only by what physics and chemistry allow. But statistics also imply something else. Something less comfortable but completely unavoidable. The more visitors that arrive, the greater the chance that some of them will not fit neatly into our natural categories. Outliers are inevitable. With a large enough sample size, anomalies will start to accumulate. And anomalies are where speculation flourishes. Imagine a comet that behaves too predictably, or a rock whose trajectory hints at some kind of subtle, non-gravitational control, or an object whose chemistry appears to be engineered rather than naturally formed. Any one of these discoveries would ignite debates that would rage far beyond the quiet halls of astronomy. The odds of these kinds of anomalies appearing increase, not because design is inherently likely, but because a vast number of objects guarantees that strangeness will eventually show up. Probability ensures not only normality, but also exceptions. And exceptions fuel paranoia just as much as they fuel discovery. This is precisely why the statistics of the infinite, the idea of a universe filled with trillions of these things, is just as unsettling as it is reassuring. On one hand, it makes interstellar visitors seem ordinary. It explains why we should expect to see many more detections in the near future. But on the other hand, it opens the door to scenarios that can't just be dismissed with a simple wave of the hand. When the sample size is, for all practical purposes, infinite, then every single possibility, no matter how small, becomes inevitable somewhere, at some time. The real question then becomes whether we will recognize it when it passes through our sky. The mathematics of this extend beyond just population counts. They also touch on the immense timescales involved. Each one of these wanderers has been traveling for millions, or in some cases billions of years before arriving here. That incredible journey means they sample different environments all across the galaxy, carrying information from regions we may never be able to reach with our own probes. When a fragment from a distant, unknown system enters the view of our telescopes, it represents not just another data point, but a messenger from a different time and a different place. Now, multiply that by the vast number of wanderers, and the implication is profound. The galaxy has been conducting a slow-motion exchange of material for as long as it has existed. Every star contributes to it, and every planetary system, including our own, is part of this cosmic flow. From a scientific standpoint, this galactic circulation is a gift. Each object that passes through our solar system is a natural probe, offering us a chance to study alien chemistry without ever leaving home. By collecting their spectra, tracking their trajectories, and analyzing how their light changes over time, we can build a catalogue of planetary processes from across the entire galaxy. In time, the statistics will allow us to see the patterns. How common are water-rich comets? How rare might carbon-dominated ones be? What kinds of stellar populations produce certain chemical signatures? The infinite becomes a laboratory, with each wanderer acting as a sample in an experiment that has been in progress for billions of years. And yet, the very same logic that delights scientists unsettles the imagination. If trillions of wanderers are drifting between the stars, then our skies are part of a galactic network of messengers. And once you frame it that way, the question inevitably shifts. If nature uses these wanderers to exchange material, might intelligence also use them? A civilization that is millions of years older than ours wouldn't need to build elaborate, energy-intensive spacecraft to send probes across the galaxy. It could simply hide them among the countless natural fragments, making them completely indistinguishable except to those who know exactly what to look for. The statistics guarantee that among the infinite, concealment is trivial. Every rock becomes potential camouflage. Every comet becomes a potential disguise. The scientific plausibility of such scenarios is secondary to the realization that the numbers allow for them. With a background population so vast, any sign of intention can simply vanish into the noise of randomness. And that is both reassuring and deeply disturbing. It means that if we never find any evidence of design, the statistics still hold up. But if we ever do find it, it will be almost impossible to prove that it wasn't just a bizarre statistical fluke. The infinite makes every conclusion provisional, every certainty fragile. This fragility isn't unique to astronomy. Statistics in medicine, in economics, in climate science, they all carry this same duality. They provide us with confidence while always leaving a little bit of space for the exceptions. But in astronomy, the stakes feel different. The infinite isn't just a mathematical model. It is the actual scale of the universe itself. A universe that is completely indifferent to our human need for clarity. Interstellar wanderers embody that indifference. Each one is ordinary when seen in a statistical context, yet completely extraordinary when it passes close enough for us to notice. The infinite reduces them to inevitabilities, but our experience of them remains singular. That tension will never go away. The lesson from all these statistics is crystal clear. More are coming. Not just a handful, but a constant stream. Once the Vera Rubin Observatory begins its surveys, astronomers expect to start cataloguing interstellar objects at a rate approaching several per year. Some predictions are even higher. The infinite is about to become tangible, filling up our databases with orbits, magnitudes, and chemical spectra. Each new detection will be another confirmation of this galactic background, but it will also be another opportunity for an anomaly to appear. And every single anomaly will test our ability to separate science from speculation. The real challenge may not be in the numbers themselves, but in what those numbers reveal about our own psychology. Humans are not naturally equipped to think in cold, statistical terms. We respond to the dramatic, the singular, the anomalous. 3 confirmed visitors in less than a decade feels like a signal, even though the mathematics tell us it is an expected outcome. 10 or 20 more will reinforce the reality of their abundance, but it will be the anomalies among them that will dominate our attention. The statistics of the infinite will reassure the scientists, but they will also fuel public paranoia, because the infinite does not erase the possibility of the extraordinary. It multiplies it. The story of Atlas is inseparable from this context. Its detection isn't just about a single comet. It's about what its existence says about the population as a whole. Its unusual chemistry could just be a statistical outlier, or it could be part of a broader category of objects we have yet to define. Only by adding more detections to our catalogue can we possibly know. Until then, Atlas embodies both the certainty of statistics and the deep unease of exceptions. It is one single thread in an infinite tapestry, visible to us only briefly before it disappears back into the void forever. The infinite ensures there will be others, but it also ensures that our uncertainty will remain. As more objects appear, the statistics will harden into confidence. The density of interstellar wanderers will be better constrained, the range of their chemistries will be mapped, the diversity of their shapes catalogued. But no amount of statistics will ever erase the shadows entirely. The infinite guarantees not just normality, but also strangeness. And it is in that strangeness that the speculation will always live. The more often these interstellar visitors appear, the harder it becomes to treat them as isolated curiosities. At first, each one seemed like a self-contained story. Oumuamua appeared, startled astronomers, and then vanished into the dark, before its deepest secrets could ever be resolved. Borisov followed, behaving much more like a conventional comet with its long tail and chemical markers, making perfect sense within our natural expectations. Then Atlas arrived, an object that somehow combined the comet-like with the completely unexpected, carrying carbon dioxide levels that stood out in ways nobody had anticipated. Individually, these stories can be contained, but taken together, they start to suggest something more. Patterns begin to emerge, not only in the objects themselves, but in the way we respond to them. These wanderers are more than just rocks and ice. They are mirrors, reflecting both the galaxy's ancient history and our own shifting understanding of our place within it. The first clear pattern is one of frequency. Before 2017, the number of confirmed interstellar visitors was 0. In less than a decade, there are now 3. If you look forward instead of backward, our models suggest this pattern is only accelerating. With the advanced surveys coming online, it won't be 3 in 10 years. It'll be dozens within the same span of time. This frequency turns anomalies into statistics. Each new detection makes the next one feel a little less remarkable. And yet, the sense of strangeness doesn't just disappear. Instead, it moves. It shifts from the mere fact of their presence to the specific details of their behavior. Once we accept that their frequent arrival is normal, our attention naturally focuses on their chemistry, their trajectory, and their structure as we search for the deeper stories hidden within the data. Chemistry provides one of the strongest hints of a pattern. Borisov resembled comets from our own solar system, but with subtle differences in the abundance of certain compounds. Its spectrum suggested it originated in a cold, volatile, rich environment, likely far from the star that formed it. Atlas, by contrast, displayed carbon dioxide in concentrations far above what our models predicted. That single detail suggests an entirely different formation history, possibly within a system where carbon dominated over oxygen or where water ice was depleted very early on. Oumuamua, frustratingly faint, left its chemistry unresolved, but its very lack of a visible coma was itself a powerful clue. If you see these 3 together, they suggest that interstellar wanderers carry the unique chemical fingerprints of their home systems in their volatile content. Patterns in chemistry become patterns in origin, helping us map the diversity of planetary nurseries all across the galaxy. Trajectory offers another layer to this emerging picture. All 3 confirmed visitors shared hyperbolic orbits, which is the definitive proof that they came from beyond the Sun's gravitational influence. But even within that category, the differences matter. Oumuamua's entry direction traced back toward the general relative motion of nearby stars, suggesting it came from the galactic field rather than any specific system. Borisov's velocity was high, but still within the range we'd expect for ejected comets. Atlas was moving faster still, raising questions about whether it had been accelerated by encounters with multiple stars, or even by chaotic interactions within a dense stellar nursery. The pattern here is not one of identical motion, but of a shared origin in chaos. These wanderers arrive not from one single place, but from everywhere, their paths shaped by billions of years of complex galactic interactions. Shape and structure add yet another dimension to the puzzle. Oumuamua's elongated form, whether it was cigar-like or pancake-flat, became one of its defining mysteries. Borisov looked like a completely conventional comet, a round nucleus, a diffuse coma, and a long, streaming tail. Atlas, though faint, showed signs of fragmentation, possibly breaking apart as it got closer to the Sunday. At first glance, these different forms seem completely unconnected, but together they sketch out a pattern of sheer variety. The diversity of their shapes is itself meaningful, reflecting the different stresses, collisions, and erosions these objects have to endure during their epic journeys. Patterns are emerging not in uniformity, but in diversity, showing us that interstellar space is a crucible of transformation. Each wanderer is both a representative of its origin and a sculpture shaped by its travels. But the patterns are not only physical, they also exist in our own reactions. The public response to Oumuamua was a mixture of astonishment and wild speculation. Its odd trajectory and acceleration led some, including respected scientists, to wonder aloud about artificial origins. With Borisov, the general mood shifted to one of relief. It looked like what astronomers expected a natural comet to look like, and it was almost reassuring in its familiarity. Atlas has now reignited our curiosity, its strange chemistry opening up a whole new set of questions. This sequence reveals a pattern in our own psychology. The first arrival shocked us. The second one soothed us. The third one has unsettled us all over again. The next one may follow this cycle, or it could break it entirely, depending on what anomalies it presents. These wanderers don't just reveal patterns in themselves. They reveal patterns in us, in how we balance our sense of wonder, our deep-seated fear, and our desperate need for explanation. One might fairly ask whether these patterns are real, or just illusions created by a small number of data points. 3 objects are hardly a sufficient sample size from which to draw firm conclusions. And yet, the human mind simply cannot resist finding structure, even where pure randomness rules. This is both a strength and a weakness. It allows us to generate hypotheses, to treat chemistry and trajectory as clues that are worth following, but it also tempts us into seeing intentional design where none exists. The idea that these wanderers might be arriving in a deliberate sequence, each one carrying a hidden message, grows naturally from the human tendency to impose order on chaos. Whether the universe is actually offering us patterns or we're simply inventing them is a question without an easy answer. From a scientific standpoint, patterns are tools. By cataloguing the chemistry, trajectories, and shapes across dozens or even hundreds of interstellar objects, we will eventually be able to distinguish randomness from a meaningful distribution. If Atlas's carbon dioxide-dominated chemistry turns out to be common, then it signals a frequent type of planetary chemistry in our galaxy. If it remains unique, then it's an anomaly that needs to be explained. The same logic applies to speed, structure, and every other measurable property. Over time, the patterns will clarify, transforming our speculation into knowledge. But until then, every single detection will hover somewhere between the two. Each wanderer is both a piece of data and an enigma, a single dot in a picture that is not yet complete. And yet, even when the patterns do become clearer, the possibility of hidden layers will always remain. The galaxy is vast and our instruments are limited. What we see will always be filtered through our technology and our interpretation. That means patterns may emerge that are just artifacts of our methods, rather than fundamental truths about the objects themselves. Selection bias, detection thresholds, and observational gaps all shape the data we collect. What appears to be a cluster might just be a mirage. What looks like a deliberate sequence might just be a coincidence. These wanderers are teaching us not only about the galaxy, but about the inherent limits of our own perception. Still, the temptation to search for a deeper meaning will not vanish. The idea that these wanderers might serve as messengers, either of natural processes or of something more intentional, lingers at the edge of every anomaly. Patterns in chemistry might one day hint at panspermia, the transfer of the building blocks of life between solar systems. Patterns in trajectory might suggest a clustering of objects around certain interesting regions of the galaxy. Patterns in their frequency might reveal epochs of increased arrivals, linked to the grand, slow dynamics of the Milky Way. Each of these possibilities carries implications that stretch far beyond science and into the realm of philosophy. These wanderers are not only physical objects, they are questions, written in fire and ice across the sky. And the patterns we find are the language we are trying to use to read them. Looking at the 3 we have so far, the most honest conclusion is that the patterns exist, but they remain profoundly incomplete. We see hints of diversity in their chemistry, stark differences in their speed, and sharp contrasts in their shape. We see repetition in their hyperbolic trajectories, and in the sheer inevitability of their arrival. We see cycles in our own human reaction to them. None of this is enough to declare any certainty, and yet none of it can be ignored. These wanderers demand our attention because they embody the intersection of randomness and structure. They remind us that patterns are not only things we find, but also things we create, shaping our interpretation of the universe around us. And as more arrive, the patterns will deepen. Some will confirm our expectations, others will challenge them. But together, they will form a picture not of a single simple narrative, but of a galaxy in constant, churning motion, scattering its fragments across the void. Each object is a single sentence in a story that is billions of years long. And each detection is our chance to read just one more line of that story. Incomplete, but endlessly suggestive. These wanderers are not accidents. They are part of the very fabric of the galaxy, and the patterns they carry are part of the fabric of us, as we try to understand our place within it.